Okay, let's take a look at this pressure loss assignment in detail. It's we're taking a lot of time to focus on this topic, but it's important. It's the last high quality check we do on an irrigation system. And there's so many terms, there's so many elements to the sprinkler system that it's difficult to wrap your head around it, first of all, and then to understand why we need to do a check for pressure loss. So I'm going to walk through the assignment. In order to do that, I'm going to share a couple of my screens. So here is the assignment as you see it. I give you the diagram. Remember, we're assuming this is the worst case scenario zone. And a zone is anything that's operated by a valve. So there's its own automatic control valve, station number, whatever it is, turns on. And it's the worst case because it has to run the farthest around the house. And in order to do that, when you go through a long length of pipe, you have a lot of friction. And all we're trying to do here is to make sure that the system will work. We want to see if there's enough pressure to make this thing work. So I give you the information up here. We're going to take a look at this. I have you looking at a system pressure loss worksheet. And then I give you information down here that these are 3 gallon per minute rotors, and they're all matched precipitation rate. So let's fill this in one at a time. Let me pull up the pressure loss worksheet. I'm going to try to keep this nice and tidy so that way I can work on both windows at once, along with filming, and make sure that we have everything we need. So an Excel version is nice because you can make it do the math for you, but you can also do the math by yourself. And I'm going to explain what each of these is because I understand it's not fully intuitive, but we want to first copy as much information from the assignment into the worksheet as possible. So and we'll just say this is project name assignment. The first thing we want to know is how much pressure is required by the sprinklers when they are turned on. Ultimately, we can figure out the static pressure of a house. When there's no water moving, how much pressure is on at the house? You hook up a little water meter, turn it on, watch the dial go, and you can figure out your static pressure. Or you can look at your elevation. Remember our little formulas for being able to determine the amount of water pressure as pounds per square inch, the weight of water above you. So we only have so much water that we can actually use, or so much pressure. And how many pounds per square inch of water do our sprinklers need in order to operate? I tell you right over here, they need to operate at 35 PSI. So we plug that number right in. Whatever our static water pressure is, when the system turns on, we are going to be 35 PSI less because we're using that with the sprinklers. So that's the sprinklers, that's the easy one. The rest of these, we're calculating any additional pressure that is lost when this thing turns on. And water is moving through all of these components. Just by moving through the components, there will be friction, and that will reduce pressure. Hopefully it's not, none of these by themselves is a whole other 35. There'll be small amounts, but it will all add up. So we need to calculate. So let's first fill in the details. Lateral pipe, type and size. I tell you it's 3/4 inch, class 200. The length, I tell you it's 130 feet. Let's ignore the flow for now. We'll look at that in a little bit. Main line, I tell you it's 1 inch, class 200, and that it's 290 feet. We'll skip over the lateral and main line fittings for a moment. The valve is a 1 inch electric globe valve. There's no length associated because it's just one little thing. There's no master valve in this system. The backflow prevention device is a 1 inch reduced pressure device. The pipe going to the backflow is 1 inch copper, and it is 5 feet. There's no main valve. We're ignoring that for right now. The pipe going to the POC, and POC stands for point of connection, which is where does the irrigation system connect to the water being supplied to the house. We call that the point of connection. The point of connection pipe is 7 feet, or sorry, 1 inch copper again, 7 feet. The water meter is 5/8 of an inch. The service line to the meter is 1 inch copper, 10 feet. So these are basically what we're doing here is we're trying to diagram all the pieces here. And I know if you look at this, it's kind of tricky because we've got a meter. It doesn't show the pipe going up to the house, but we've got a main line coming off here, a backflow prevention device, goes all the way around. And I gave you the dimensions, so you don't need to be worrying about trying to measure this thing. Just, this is more for conceptual purposes. But we do need to look at this for our next bit of information we need to figure out, which is our flow. We need to know how many gallons per minute are flowing through this system when this zone is turned on. So here we have medium rotors, 3 gallons per minute for a full circle, and that they are all matched precipitation rate. So what that means is if you have a half of a full, it's going to be half of the gallons per minute because we want the precipitation rate to be the same. We don't want to be adding, if they were all 3 gallons per minute, then the half would be adding twice as much as the full. Does that make sense? So by matching the precipitation rate, then a full will be putting out a certain amount in a full circle. And if you cut that in half, you're putting out half as much water, not the same amount of water in half the area. Match precipitation rate means that here, if we count up all of the gallons per minute for each rotor, we will get the total flow for the zone. And match precipitation rate means we got to do a little bit of math. So we've got 3. And then we have a half, which will be half as much water. And so what's half of 3? 1.5. So here's another 1.5. So we've got 6 in total on this side, gallons per minute. Down here, we've got 0.75, 0.75, 1.5. So what does that equal? 3. So total, we are at 9 PSI. So I'll just double check my math. We've got 3, 6. I believe the book says 12, but they just duplicated this wing without remembering that this is literally 50% of the upper one. So we've got 3 on this branch, 6 here. So we're at 9 total. So our flow is going to be 9. And we add 9 gallons per minute to all of these things. I'm skipping over the ones where we don't need to have any calculations. Okay, getting more info. Now, the friction factor is where we have to consult the friction loss charts. And so if we go up here and take a look, we click on all of these links, that will tell us what the friction factor is. And if it's pipe, we're measuring it for every 100 feet. So let's take a look. We'll do it in order. The lateral pipe is class 200 PVC. So I already have the tab open here. We look at class 200 PVC. And our flow is 9 gallons per minute. So we go over here to 3/4 inch. And at 9 gallons per minute, the friction, the pressure loss, friction loss is going to be 3.94. 3.94 what? PSI for every 100 feet of pipe. Okay. So we take that and we say 3.94. We'll do the calculations here in a little bit. Now this same chart will give us the 1 inch main line. So 1 inch class 200, I've got it right here. At 9 gallons per minute, it is 1.17 PSI lost per 100 feet, 1.17. Okay. I'm going to skip over the fittings for a moment. Let's look at our zone valve. And here we have it. Pressure loss through globe valves. What are we? We are 1 inch globe. So what's our flow is 9, somewhere between 8 and 10. The chart only shows 8 or 10. And it's either 1 or 1.5. So let's go in the middle and say 1.25. Zone valve, 1.25. And actually, because this is not pipe, we'll just do the actual pressure loss, 1.25. We're going to total up this column. So this goes in the subtotal column. So when this turns on, when this valve turns on, the 1 inch globe at 9 gallons per minute, it's going to, the water going through the valve is going to lose 1.25 PSI. Now we need the backflow prevention device. We've got a 1 inch reduced pressure assembly. And if we look at our flow rate of 9 gallons per minute, it's pretty low. It's so low that this 1 inch doesn't even register. So that would be an area where you may tell the designer, if you are the designer, you may consider resizing. Or if you took a look and you're going to say, well, we're going to have multiple of these on at a time, we still will have the high flow rate, keep it 1 inch. We're going to just assume 12. Doesn't go down to our PSI range. At the size down, it's a little less than 12. We're going to say 12 just to be on the safe side. And again, the fact that it doesn't match or it's not listed on the pressure loss chart is an indicator that it may be a problem with the selection. You may want to go and see, why did we choose 1 inch? But for the purposes of determining the pressure loss, we're going to assume these are the proper sizes and we're going to calculate it as designed. So we've got 12. 12 PSI is lost when water flows through the backflow prevention device. Now we've got the pipe going to the backflow prevention device, and that is 1 inch copper pipe. So we open the friction loss chart for copper. We find 1 inch right here, and we're at 9 PSI. So 9 PSI, 1 inch. The loss for every 100 feet, remember, is 2.9. 2.9. Okay. Skipping over the main valve, the pipe to the point of connection also is 1 inch copper. So it still is 2.9 for every 100 feet. And this service line to the meter, also 1 inch copper. We're going to put 2.9 there again. Now, all we have to do is consider how much pressure is lost when the water flows through the water meter. Because remember, these are all the pieces in line, and we just need to measure how much pressure is lost in each of them. And we have a 5/8 inch water meter at 9 gallons per minute. So here's 5/8, 9 gallons per minute. We have 3 PSI. And because it's not pipe, it's a fixture. There's only one of it. We are going to put it in this column, 3 PSI. Okay. So now, hopefully you can understand how to read the charts and be given a set of components, their sizes, their lengths, and determine the flow of a station by looking at the emitters, the heads, the rotors. We want to see, okay, how many gallons per minute, and then we use that information, look at a friction loss chart for that type of pipe or fitting, and then we copy down how much pressure is lost, either in a length of 100 feet of pipe or in the fitting itself. We take all that information, we write it down. We put it here on a chart, kind of like this. Now, I'm going to do a little bit of math here with Excel, and I'm going to do that for the purpose of helping to show you exactly the kind of math that we're going to do. And it's tricky to do math on camera sometimes. And so when I use Excel, it's nice because it's going to make sure I don't make silly mistakes. But we're going to need to take a look at this lateral and mainline fittings. And also, we're going to need to add the pressure loss for the actual amount of pipe. And let me just consult my notes here. Okay, So here's how we're going to do this. A couple different ways you could do this calculation. And I'm going to use the formula function in Excel. Hopefully that's not too confusing and pretty easy for you to follow. This amount, 3.94 for our lateral pipe, is the amount of pressure lost for every 100 feet. But we want to know how much is going to be lost for 130 feet. It's pretty easy to figure this out. All we have to do is divide by 100. So we would figure out how much would be lost for every 1 foot, and then multiply by the length to determine how much is lost for the actual amount. Okay, so we take whatever value was put in here, 3.94, the value of E6, we're going to divide that by 100, because I want to know how much PSI is lost for every foot. Now, I'll take that and I'm going to multiply by 130 over here. That's going to give me 5.122. And I'll just bring it down to, I'll round it to the 2 decimal places. So do you see how that works? And you always want to check your logic. Okay, so this is almost 4 PSI for 100 feet. And I'm going to have 130. So it's going to be a little bit more than 4. It's going to be 5. All right. Just make sure you double check your logic. We're going to do the same formula for this main line right here. And in order to do it in Excel, I just drag it down and voila, it takes the same formula, but applies it to these boxes instead. So don't get confused by if you're not familiar with Excel, don't get confused by what I'm doing. It's basically like using a calculator. So now we want to check our math. For every 100 feet of 1 inch class 200, we're going to lose about 1 PSI. And we have 290, which is almost 300 feet. So we should be losing about 3 PSI. We double check. There we go. 3.39. All right. Now we want to, that's just pipe, but the pipe is going to be connected with a bunch of fittings. And it's too complicated to try to calculate every single little fitting. So we just take 10% of whatever is the lateral and the main line. We take 10% of that. And I could do it in a formula, but I'm just going to try to separate it out so that you can see exactly what I'm doing. I'm going to add the amount for our lateral and our main line pipe. And that comes to 8.52. I just want to remember later, I'm not going to count this in my calculation, but I'm doing it just to show you what, how to get this amount. And now we're going to take the 8.52 and we're going to get 10% of that. So we're going to multiply by 0.1. We'll round this to 2 decimal places, and that gives us 0.85. So could also just move the decimal place 1 point to get your 10%, 0.85. Does that make sense? You check yourself. 1 is 10% of 10. So a little less than 1 is 10% of 8.5. Okay, we're looking good and we're filling in the column. No master valve. Oh, didn't mean to do that. No master valve. We've got our backflow prevention device. We need to do the pipe to the backflow. So it's the same thing. We take the pressure loss for every 100 feet. We divide by 100 and we multiply by the length. I get 0.145, or if I round it, 0.15. Does that make sense? It's really small. Yes, it makes sense because 5 feet is very small compared to 100. So we're going to have a much smaller amount than the 2.9 listed here. Got no main valve. How about the point of connection? Can actually just copy the formula here and put it down here and put it down there. And you can see I end up with small amounts for each of these situations. There's no elevation gain. And so now we've calculated how much pressure is going to be used when the sprinklers are turned on from the sprinklers themselves. And we've also calculated how much extra pressure in the water will be lost just by running through all the pipes and the fittings. This is why your worst case scenario zone is usually the furthest distance, because the length of your pipe matters here. And so we need to add all of these up. So to get the total, we take our 35. We're going to add each of these elements. I'm going to skip over this because remember, I just did that to help me figure out the 10%. That's not an actual piece of this puzzle. I would be counting it twice if I included the 8.52. Add up everything here. And the grand total is 61.25 PSI. And we're going to round that to an actual value. There we go. Our final system pressure loss is going to be 61 PSI. So there you have it. I hope that walkthrough helps you to, first of all, see how the calculations are done, but more importantly, how do we take the data, the friction loss charts, and apply them to an actual scenario? And remember, the whole point of this is to make sure we're not going to use too much pressure. First of all, that there's enough pressure to supply to the system, and also that we're not going to rob everything in the whole house, because it would be, in this case, it's residential, but even if it's commercial or anything else, you never want to use 100% of your pressure, because then no one can flush a toilet or turn on a sink or whatever else they'll be doing. And I hope you can see now why it's important to know what is your worst case, because we could technically do this same calculation for every station, every single zone on the design. But it's pointless if we calculate the worst case scenario and we say, okay, it's going to lose 61 PSI. And if that is acceptable, then all the other ones, which are going to be primarily shorter in pipe, those will also be acceptable, because the worst case is going to have the most pressure loss. And so that's why you only need to do one calculation, but you do need to consider all the pieces, even going all the way back to the water meter. And it's not a lot of pressure that you lose in your water meter, but did you notice how much difference there was between the 35 operating pressure and the 61 required? There's a lot of other components and they add up. And so that's why we need to kind of always be thinking about the different pressure elements, the sizes of our components, And at the very end, if we've got a good design, we can cross-reference with our pressure loss test. Now, let's say that that was too much pressure lost. If that was the case, what would we do? Well, do we have to just scrap it and start from scratch? No, we can keep all the components in the same place. All we need to do is change the pipe size. So did you notice how the smaller the diameter pipe, the more friction? If you go up in size, you have less friction and it can still handle the flow. Why don't we just size it up in the first place? Because it's cheaper to use smaller size pipe. And as a designer, your job is not necessarily to tell them the best size. Your job is to specify the proper size. So what is the minimum pipe size for the given area? And you look at the total picture to figure that out. If you were losing too much pressure, we would up some pipe sizes or maybe even change one of those sizes of those fittings and get ourselves into an optimal range where we're losing an acceptable amount of pressure. So hopefully this helps you to think through the assignment, to understand how to do it, but also to understand why it's important and how it's kind of the final check in the system, because we've got all the elements placed. We've got everything sized so that it can actually apply the water the way it is supposed to. And now we just need to make sure we're not going to rob too much pressure from the overall system. Hope you enjoyed this little walkthrough and explanation of how to perform a system pressure loss test. Thank you.